Hello, Waterloo Engineering alumni. We delivered this engineering research talk at Reunion on June 1st, 2024, in front of a live audience of engineering alumni in the Engineering 7 building on main campus. However, due to poor sound in the lecture hall, we are re-recording this research lecture for you today, which will ensure that presentations of the highest quality are available to you. And so the idea for today was to introduce you to some of the fascinating and impactful research that our newest faculty members are undertaking and to show how this work relates to some of the institutional goals at the University of Waterloo. In 2022, our president, Vivek Goel, outlined a strategic vision that looked to answer a fundamental question. What do we as an institution aspire to be known for by our 100th anniversary in 2057? The answer, in short, is that we aspire to be known for taking on and solving the biggest, most complex challenges facing humanity and our planet. The global futures that we will discuss today are a way of conceptualizing these challenges so that we can organize and take them on. We have identified 5 interconnected futures for humanity: societal, health, sustainable, technological, and economic. These futures, aligned to our academic and research strength, help us to focus and coordinate our work across disciplines and organizational boundaries. Today, each of our speakers will present research that connects with one of the global futures. They will talk for about 5 minutes about their work, and then there was an opportunity to answer questions at the live event. There won't be, unfortunately, at this. Now, I'd like to welcome Veronica Magdas to talk about health futures. Veronica is an assistant professor in the Department of Systems Design Engineering. Her main research is in microrobotics for medical applications. This includes biohybrid approaches, including harnessing the functionality of cells and other biological components to create innovative solutions in medicine. She will be sharing some of the ways in which the design of microrobotics can draw inspiration from the natural world. Welcome, Veronica.
Thanks for the introduction, Dean Wells, and I'm honored to present my research here to the alumni today. So we work in the field of biomedical engineering, and specifically we're aiming at developing bio-inspired artificial microrobots for medical applications. And the purpose we are targeting is to tackle some of the most important global health issues. For example, cancer, because most of the current treatment methods are not very targeted and effective. And in fact, only 1% of cancer drug reaches the tumor site, which shows how ineffective the method really is, and the problem that we see with many side effects because we have a systemic drug administration. So current methods are not very targeted. They don't have any active delivery strategies, and it has many side effects. And among others, also cancer treatment often affects fertility and leaves patients infertile after radiation and chemotherapy. Another issue is that it is very hard to deliver cancer drugs to the target sites because the drugs have to cross biological barriers. There are other challenges such as metastasis or invasive surgery that we need to remove tumors. Another global health issue that we are targeting with the development of microrobots is infertility. And in fact, that is also a growing issue that affects about 1 out of 6 couples. And so our question is, how can we develop less invasive techniques to target cancer and also to help in the reproductive medicine in a way that we can deliver drugs or cells locally and actively? And that's where micro-nanorobots come into play. What are micro-nanorobots? In principle, we define them as having autonomous motion, so they have some sort of onboard power source to move them. we are able to remotely control them, for example, through magnetic fields or electric fields or other remote modalities. And of course, they're only robots if they can perform certain tasks. And these tasks that we are targeting are cell and drug delivery, cell manipulation, minimally invasive surgery, and diagnostics. So the first approach that we undertook, or that I undertook over the last decade, was to develop different motion mechanisms that function on the microscale, because we cannot just downscale macroscopic propulsion mechanisms. We have to think of completely different mechanisms, because the physics on a microscale are quite different. So as an example here, what we see in the first video is a polymer that responds to small temperature changing by changing its shape. So this is completely artificial, but it's a bio-inspired mechanism that mimics the motion of a jellyfish. The second robot you see in the center here is actually catalytically driven. So it's driven by chemical reactions and makes this little tube move very, very fast. And in fact, these microjets made it into the Guinness Book of Records for being the fastest microjet engine on Earth. The last mechanism you see here on the right actually uses active cells. In this case here, we see bull sperm that are actively moving, and they are very well designed to swim on the microscale because they have evolved over millions of years to function well in physiological environments. So here we see the micro swimmer, the sperm cell, being trapped in a microtube and then start pushing this microstructure around. So the idea is that we can combine artificial microstructures by the use of nanotechnology. We can fabricate these and then use different strategies to move them, either by shape change, by reactions, chemical reactions, or by motor cells. And another example of microrobot motion can be generated by using sperm cells as templates, as structural templates, and covering them in magnetic nanoparticles. This is what you see here in the scanning electron microscopic image on the left. And then we can, after attaching the microparticles to the sperm cells, we can actuate them by exposing them to rotating magnetic fields, as you see here on the bottom. This is actually a non-motile cell, but in response to the magnetic field, it rotates, and we can see it moving forward as we increase the frequency of this rotating magnetic field. So here we are not dependent on the lifetime of the sperm or the motility of the sperm, but we have full control over the speed and the direction by exposing them to rotating magnetic fields. And what do we use these microrobots for? We can load them with cancer drugs. We can also cluster them and use this to make them visible in ultrasound or X-ray fluoroscopy, which means we can use these microrobots to track sperm cells in the reproductive tract, but also to deliver drugs in a very localized manner in the reproductive tract. So these types of microrobots are currently being explored for drug delivery and diagnostics in the reproductive tract in a non-invasive manner. The next slide here, I want to share with you an approach for bio-inspired microrobots. So here we have completely artificial robots that are in the millimeter scale. So you see here this filament moving that has a small micromagnet embedded, and it is also loaded with enzymes. And this particular purpose that we have for this microrobot is targeting kidney stones in the urinary tract. So the idea here is that we can circumvent surgery, also circumvent oral administration of drugs that aim to increase the pH of urine to either prevent kidney stone formation or dissolve kidney stone over time. This is very difficult currently with oral administration, but with the help of these small filaments, we can locally deliver enzymes in a high concentration and support the dissolution of kidney stones. So far, we can see in our preliminary study that we can locally reduce the stone size and thereby support a faster kidney stone dissolution. Another example here is a slightly different structure. So we here have, again, a magnetic microrobot, but in this case, it is a screw-shaped robot that has a micromagnet in the center as well, and responds to rotating magnetic field once more. And in this case, we're aiming at tetherless blood clot removal. So you can see here, we are trying this in an ex vivo model of the renal artery of a pig. And the idea is to mechanically disrupt blood clots that are currently hard to reach with catheters, and help us to restore the blood clot, restore the blood flow quickly. So as a summary, we aim at different potential applications of these medical microrobots that range from precision cargo delivery, such as cell delivery or targeted drug delivery, also to novel technologies for reproductive health. So we also look at diagnostics of sperm cells and diagnostics to understand sperm migration and understand reasons for infertility better. Also developing robots for non-invasive reproductive assisted technologies such as non-invasive ovum pickup or embryo transfer. And of course, these non-invasive surgical tools for the removal of occlusions such as blood clots, kidney stones, or other techniques where we're aiming at developing non-invasive tetherless action of these robots. So with that, I'd like to thank you for your attention, and of course, thank the funding agency that support this research, and of course, all collaborators and team members that make this research really fun and successful. Thank you for your attention.
I'd like to now welcome Michael Benoit, Assistant Professor in the Department of Mechanical and Mechatronics Engineering, to help us frame technology futures. Michael's research spans many topics in the fields of welding and joining and metal additive manufacturing. Michael works closely with the newly opened MSAM, our multi-scale additive manufacturing facility, and this is one of the largest research and development additive manufacturing facilities in the entire world. His talk today will highlight the use of additive manufacturing technologies to repair high-value metallic parts for the automotive industry, resulting in more competitive and sustainable manufacturing. Welcome, Michael.
Thank you for the introduction, Dean Wells. Hello, everyone, and welcome back to campus. My name is Michael Benoit, and I'm an assistant professor in the Department of Mechanical and Mechatronics Engineering. And today I'm going to talk to you about a revolution in manufacturing. But before we talk about that, let's first take a look at the manufacturing sector in Canada. Now, it turns out that manufacturing is a vital part of our economy, contributing about 10% of our GDP and creating up to 1.7 million high-quality and relatively well-paying jobs. Now, when we look at the breadth of the manufacturing sector, it touches on many different industries, from transportation to textile production to medical and biomedical manufacturing and the production of hydrogen and fuel cells, just to name a few. But similar to almost every other industry and sector, there's a need for continual innovation in order for the Canadian manufacturing sector to remain globally competitive. And one example of an innovation or a recent innovation in manufacturing is what we call additive manufacturing, or more commonly referred to as 3D printing. Now, what additive manufacturing is, it's essentially a host of related technologies, all of which seek to produce a part geometry by taking a digital model of the part, slicing it up into thousands of different layers, and then creating a tool path where we're depositing material only where it's necessary by the design. As I mentioned, when we talk about additive, we're talking about a host of different processes, which are all take this layer-wise approach to manufacturing, but they differ based on the types of materials that they use, so whether or not it's metals or polymers, as well as the heat source used to consolidate those materials. So we could be using a laser, an electron beam, an electric arc, or many other different consolidation processes. But generally speaking, when we talk about additive manufacturing, these processes tend to offer us many benefits and opportunities compared to traditional manufacturing processes. So this could be things like creating highly complex or highly geometrically complex parts that we couldn't produce by any other conventional manufacturing method, which greatly expands our design freedoms and allows for highly customizable parts as well. It also allows us to reduce waste during production because we're placing material only where it's needed within the design. By also printing our parts in one machine, it allows us to consolidate many different processes to create near net shape parts and allows us to reduce factory footprints as well as warehouses and inventories. The process can also help us accelerate product development cycles and reduce our time to market. And some processes, one of which I'll talk about today, also allows us to not only print brand new parts, but allows us to repair, refurbish, and clad existing high value components. So this is really the promise of additive manufacturing, the ability to create highly complex and advanced components that we couldn't produce by any other method. And what we can see on the slide here is just the scope of additive manufacturing in terms of what we can produce. So it gives an idea of the scope of the industry. So going from construction with the fabrication of this bridge to aerospace, to biomedical applications. It gives an idea of the complexity as well as the size of parts that we can print, from these complex lattice structures that fit in the palm of your hand up to large bridges that span canals in Amsterdam. And it also gives us an idea of the scope of materials that we can print. So just within the realm of metals and alloys, we can print anything from steels and stainless steels to nickel superalloys, titaniums, aluminum alloys, and now also copper. But despite the importance of the manufacturing sector to Canada and the opportunities that additive manufacturing present to us, there's been a surprisingly limited and slow adoption of these technologies by Canadian industry. And several different reasons have been cited for this, and we can see a few of these on the right-hand side here. But in my opinion, there's one specific type of additive manufacturing process that we can use to make an immediate and very meaningful impact for many industries and companies right now. And that's the process that we refer to as laser-directed energy deposition, or laser DED. And that's because the laser DED process allows us to not only print new parts, but repair, refurbish, and clad existing metallic components. And here on the bottom of the slide, we can see a number of different applications where we're using this technology to refurbish, repair, and clad components. So for the rest of the presentation today, I'm going to just give a very high-level overview of a case study that some of my students have been working on. And through working through this case study with an industry partner, we've also addressed a number of the challenges that have previously been cited, namely limited part quality, the lack of business applications, and a shortage of highly skilled talent. Okay, so let's take a look at this case study. So here, what we're doing for this project is we've been working with an automotive parts manufacturer, and they currently have a piece of tooling that's which we call an insert, and it's used in a high pressure die casting application for aluminum components. Now the part, or the insert itself, is made from what we call a martensitic steel, a very, very high strength, high hardness material. And this insert has a very complex geometry. So between a very difficult to machine material and a highly complex geometry, it was also an ideal candidate to be produced by a different type of additive manufacturing called laser powder bed fusion. Now, this insert costs the manufacturer about $25,000 per insert. And when I talked with the company, they told me that after so many casting cycles, these inserts tend to crack, at which point they must scrap the insert. And they go through 20 to 25-ish a year. So we're looking at about $500,000 to about $600K a year in operating costs just from this single insert. And so what I told the company was, why don't you send me this part and we're going to look at repairing it by using laser directed energy deposition. So here what we can see is a small segment of this tooling geometry, or the insert geometry. And the overall insert's about 1 foot long and weighs about 40 pounds. And as I mentioned, it's highly complex, but here we can only show a small part of that geometry. But when we zoom in, we find this little micro crack that's causing the company to scrap this part. And here in this scale bar at the bottom of this image, it's about 2 millimeter wide. So you can see just how narrow this crack is. But nevertheless, when it cracks, the manufacturer is required to scrap that part. So they then sent the part to me, and the first thing we did is we fully removed the crack using a standard mill. So we just dug that crack out in order to prevent the crack from continuing to grow into the insert. Once we dug the crack out, the next thing we did is we used a laser scanner and we scanned that groove geometry, and we compared it with a digital CAD model of the original insert geometry. And we were able to create this green area here, which we're calling a negative space model. So that green area is the negative space, or essentially the amount of material we remove by machining. We then use this negative space model and we actually input it into the laser DED system software. And once it was in the software, we acted like this was the part to be printed. And so the software took this geometry and sliced it up into many different layers. We can see that here in this yellow model. And it created a tool path, which would tell us where we're going to be depositing the material. So on the right here, we can see the laser DED setup. There's our groove. Here's our what we call our deposition head, where the laser and powder are going to be shot out of. And on the right-hand side here, we can see a video partway through that repair process. So here's our laser and powder, and we're just depositing material to backfill that groove. Now the overall repair time for this was just about 7 minutes, which is pretty fast. So here's an image of the repair geometry. So that's the external surface. We can see a little bit of roughness because of the printing, but we can always go back in and touch that up with a mill again to get that nice smooth surface finish. We also scanned the part again after printing with a laser scanner to make sure we didn't have any substantial distortion in the part. And what we found was that there was none. The red area you can see here is because of surface roughness. So very minimal distortion, which is great. And then here is a cross section that we took through this repair geometry. And what we can see here is the darker region. That's an original insert material. And then this large U shape here was where we performed the repair. And overall, a pretty good job. So we were able to show that this is at least a feasible repair process. So at the end of the day, the first thing we did was we showed the company that using additive manufacturing, and more specifically laser DED, we could potentially save the company around about $500,000 a year just from repairing this single insert. So we helped them to develop this business case for additive. The other thing we did is through this process, we had about 8 different students who all had some part in contributing to this project. So we're increasing the number of highly skilled personnel that are required to transfer the knowledge from the lab to industry. And so the last question here is laser DED repair really this simple? Of course, in reality, it's not so simple as I've shown here. There's still many challenges that we need to address. So for example, starting over here, one of the things we need to do is further optimize our laser DED process parameters to remove any defects that we can see after printing. So here we can see, well, we have a lack of fusion between the repair material and our original insert. We also found that we can have substantial microsegregation of alloying elements and the formation of brittle compounds. So here's an example of a titanium inclusion within our repair. And so that's, of course, not desirable. So we're looking at ways to get rid of those. Up here, we can also see we have multi-phases that are forming in our material. And this is what we call our heat-affected zone. And here, instead of just having a purely martensitic structure, which is hard and strong, we're actually forming some softened phases, what we call the austenite. And then we're also looking at how can we manage to handle differences in mechanical properties, in this case hardness, between that repair region, which in this case is relatively soft, and the original parent material, the insert, which is very high, very strong. And of course, this is where we really need the real hardcore research, is to address many of these fundamental and applied problems so we can be sure that once we give the company back this insert that's being repaired, they can be very confident they can put this back into the casting line and expect a high level of performance from that insert. And so just with that, I'd like to just take a moment to thank the people who really did the real hard work on this to make all this possible. The main person being my master's student, Chris Paul, who's currently at the University of British Columbia, where I was previously. One of my postdoctoral fellows, Dr. Alistair Jones, a visiting student we had working with us, Dr. Josef Vincic, and our industry collaborators, Dr. Rob and Dr. Glenn. And over here, you can see an image of me and Chris here in the middle, and Alistair holding the insert after the first time we ever repaired it, repaired that insert. We're all quite happy with the outcome of that repair operation. And so with that, I'll end my talk. Thank you all for your attention, and I'm happy to take any questions that you might have by email. So thank you very much.
Last up is Professor Horatio Morgan to help us think about economic futures. Horatio is an associate professor of international strategy and entrepreneurship in the Conrad School of Business and Entrepreneurship. His research aims to help business leaders and policymakers forge new pathways to global expansion, innovation, and sustainable prosperity in a complex and dynamic world. Welcome, Horatio.
Thank you for the introduction. It is such a privilege to participate in this session. And I hope that we can use the next 5 minutes or so to share some ideas around the theme of closing the Canada-US business performance gap. If we have some time, we could also look at strategies and policies for driving and profiting from innovation in 21st century global value chains. Let's start with this question together. Is a business underperformance problem holding Canada back? Now, that's a great question. And we do have some good news to start with. After all, Canada has top performing global companies in natural resources, manufacturing, information technology, and other industries. But we have to be honest. There are significant opportunities for improvement, at least when compared to American firms. For sure, we are at a competitive disadvantage in crucial areas, such as research and development, and the ownership and commercialization of data and intellectual property. We perhaps could make an even stronger point by suggesting that Canadian companies must improve the scale of and returns to innovation and international operations structured by global value chains. And to be clear, by global value chains, I'm suggesting networks of interdependent companies that jointly transform inputs into outputs for consumers. Now, while making these observations, we should be mindful of the historical origins of the underperformance problem. I imagine you might think to yourself and perhaps even ask me if you could, what about past economic subordination? And if you ask that question, I hope you would go back with me to the 16th century. When you get there, what you will find are royally chartered English monopolies that organized and led textile and merchant shipping value chains under coerced and imbalanced trade flows across the English colonies, including Canada. Bearing that in mind, we can make a more forceful point by suggesting that Canadian companies are historically less incentivized than their American peers to profit from innovation in global value chains as anchor firms or as specialists in high value functions. Consider, for example, the automotive sector value chain. Of course, you are perhaps familiar with top companies such as Magna and Linamar, but they are primarily at the lower end of this chain as upstream specialists. And of course, the chain is pretty much controlled by American and Japanese automakers. The story isn't much different if we were to switch to the smartphone global value chain. Perhaps we had a chance to play in this space many years ago at the heights of success for BlackBerry or Nortel, but today this chain is firmly under the control of Apple and other anchor firms. We could go on because there's a lot to think about, but one thing we can see now with certainty is that we need a more strategic approach to innovation. And I could add, this approach ought to be more responsive to the shifting distribution of value-added contributions in global value chains. Consider the smile curve with me. And to be clear for everyone, by smile curve, I am referring to a graphical representation of the relationship between global value chain functions that companies perform and the share of value-added contributions that they receive. There are two notable observations to make here. The first one is that intangible assets are indeed more valuable than tangible assets in the 21st century than the 20th century. And by intangible assets, I'm referring to data, AI, and IP assets. Another observation is that the returns to intangible assets are relatively high when they are deployed in innovation functions that involve R&D, design, and that's at the lower end of the value chain, or in marketing and distribution at the upper end. Now, you must be thinking, this doesn't sound great. What can we do to help? In other words, what strategies and policies can improve Canadian companies' intangible asset holdings, their strategic positions, and innovation returns in global value chains? I wish we had more time to do a very good job here, but what I can say at this point is that an essential business strategy mix should include these strategies. Let's start with a competitive strategy. Do we have a strategic plan for achieving and sustaining a competitive advantage based on valuable intangible assets? Go on to the innovation strategy. Is there a plan for developing, owning, and commercializing valuable data, AI, and IP assets? And of course, we can't stop there. We have to think about a chain upgrading strategy. After all, we need to find a way to specialize in high-value functions and improve our strategic position relative to the anchor firm position. The strategy space is even more complex because we have to think about a mix of ideal strategies along with complementary institutional changes. But for sure, we have to think about policies around innovation and entrepreneurship And while we're there, we have to also consider policies that can make a difference for chain upgrading and development, competition, foreign direct investment and partnership, as well as trade and immigration policy. I wish I could say more, but this is perhaps a good place to stop. But for sure, the conversation must continue beyond this session. Thank you for listening.